Good morning friends, welcome back to Parnika tutorials. In the last video, I have discussed what is an independent process, what is a cooperative process. Then I have discussed what is the need for process synchronization. I hope you have watched that video. If you did not watch that video or if you don't know those concepts, I request you to go back and watch that video and come back to this video. In this video, I want to discuss in detail about critical section, race condition and what is the requirements for a process synchronization mechanism. So I request everyone to watch the complete video for better understanding. First, let me define what is a critical session and race condition. A critical session is a code segment where the shared variables can be accessed. Let's take that you have two processes such as process P1 and process P2. Is it clear? Now let's take that you have a shared variable and its value is some 6, okay, and then in that process you have written somewhere count plus plus, and here you have written count minus minus, and then later you have used count is equal to count into 2. Here you have written count is equal to count into 3, something you have written the instructions. Now here also you are sharing the count variable, and here also you are sharing the count variable, and here also you have using the count variable, and here also you are using the count variable. So in the process P1 and process P2 you have several instructions, and these two processes are sharing something, so we can call them as cooperative process. And the shared variable you are accessing at multiple places, so this part we will call it as critical session for the process P1, and this is another critical session for the process P1, and this is the critical session for the process P2. Is it clear? Remember one thing, a lot of students will confuse one thing. A process will have only one critical session. No, wherever you are accessing the shared variable or shared resources, then that part we will call it as a critical session. So it is a code segment where the shared variables can be accessed. So whenever you are accessing the shared variable, that part we will call it as a critical session. Is it clear? I hope you have understood. And whatever the part you are not accessing the shared variable, that part we will call it as non-critical session. Is it clear? So this part is a non-critical session, and this part is another non-critical session, and this part is another non-critical session. And similarly for the process P2, this part is a non-critical session, this is a non-critical session, and this is a non-critical section. Now let me discuss what is a race condition. The output depends on the order of instruction execution. In the last video we have discussed. Let me give an overview about it. Let's take that we have a count variable is equal to 5. Okay, you have process P1 and process P2. And process P1 you have instructions move count comma R0, okay, and then you have increment R0, and then move back R0 to the count. This is one instructions are there. So this is instruction 1, this is instruction 2, this is instruction 3. Similarly, if you write move count comma R1, okay, in the process P2 you have decrement R1, then you are moving back whatever the value which is there in the R1 to the count variable. Okay, now if you execute them in the serial order, P1 is executing instruction 1, instruction 2, instruction 3, then process P2 is executing the instruction 1, 2, 3, then final result will be count is equal to 5. Similarly, if you are executing all the instructions of P2, then P1, then also your final result of the count variable will be 5, because at one place you are incrementing, at one place you are decrementing. So if you are incrementing, it will become 6. Again, if you are decrementing, it should become 5. That is what the data consistency. Now let's take that you have executed 2 instructions of process P1 and 3 instructions of process P2. Then again you are executing the third instruction of process P3. Then what will be the count value? The count value will become 6. Is it clear? Are you able to understand? Similarly, let's take that you are executing 2 instructions of process P1, 2 instructions of process P2. Are you able to understand? again you are executing. Let me write here count is equal to 6 in this case. Now if you are executing third instruction of process P1, then you are executing third instruction of process P2, then final result of the count value will be 4. Is it clear? So if look at here, when you are executing like this, count value you are getting it as 5, and when you are executing in this order, the count value you got 6, and if you are executing in this order, the count value become 4. So the output depends on the order of instruction execution. This scenario we will call it as race condition. I hope you have understood. Now this race condition is a problem for us. Are you able to understand? Now how can we overcome this race condition? Is it clear? Now how can we overcome is that we will discuss. This can be overcome with the help of synchronization mechanisms. Okay, now look at here. Let me erase it properly. I hope you are enjoying with my videos. If you really like my videos, please press the like button and share the videos with your friends. Before sharing the videos with your friends, first you watch the complete video. Okay, now look at here. Why this race condition problem came? Now you have the critical session. Okay, there you have instruction 1, instruction 2, instruction 3 of process P1, and then you have a critical session. You have instruction 1, instruction 2, instruction 3. Now what is happening? This is a shared code. Am I right or wrong? Count plus plus, and here it is count minus. So count variable is shared. Now in this critical session, some process P1 while executing, when it is preempted, process P2 came and executing. That's why data inconsistency came into the picture. That scenario we will call it as a race condition. So how can we avoid the race condition is, any synchronization mechanism should provide the mutual exclusion. Is it clear? What is meant by mutual exclusion is, to the critical session, any one process can enter at a time. Is it clear? If only one process can enter and execute the critical session, then another process can go and execute the critical session. Now what will happen? Let's take that this is a critical session 1, 2, 3 instruction. When the process P1 enter, it should complete these instructions and then it should leave. Then only process P2 can enter. Let's take that when process P1 has been preempted, then what will happen? Process P2 should not enter. Am I right? It is leaving, but the main point I want to say here is that when the process P1 is in the critical session, process P2 should not enter into the critical session. This concept we will call it as mutual exclusion. If you design a synchronization mechanism which provides the mutual exclusion, then you will not face the race condition. Is it clear? So this is the one of the requirement of any process synchronization mechanism. So any process synchronization mechanism will write a piece of code before the critical session, and will write the piece of code after the critical session. So this part we will call it as an entry section, and this part we will call it as an exit section. Is it clear? So whenever the process P1 has entered the critical session, the synchronization mechanism or the entry section of the process P2 will restrict the process P2 cannot enter the critical session. Is it clear? Once the process P1 comes out from the critical session, then only process P2 can enter. Is it clear? So this is the first requirement of any process synchronization mechanism. And the second requirement of a process synchronization mechanism is it should provide the progress. Is it clear? Meaning is that, let's take that process P1 is not entering the critical session. Then it should not restrict, your process synchronization mechanism should not restrict process P2 to enter into the critical session. What we are saying, in a critical session, only one process can enter. If process P1 has entered, process P2 has to wait till the process P1 has left the critical session. Now let's take that process P1 is not entering the critical session. Then your synchronization mechanism should not restrict the process P2 to enter into the critical session. Is it clear? Are you able to understand? Let's take that. Okay. Now let's take that there is a mess. Okay. There is a mess is there. Okay. in some institute, let's take that seniors are there and juniors are there. They have kept a restriction to avoid the ragging. Is it clear? They said seniors should go to the mess. Once the seniors are there in the mess, is it clear? Juniors cannot enter. So this one we will call it as a critical session in that institute. Means they are saying this is the critical point. Here the ragging may happen. So once the seniors are there in the mess, juniors cannot enter. Similarly, when the juniors are there in the mess, seniors cannot enter. Now let's take that. On a particular day, seniors are enjoying the party. So when the seniors are enjoying the party, they are not going to the mess, they are doing the party somewhere. But the seniors should not restrict the juniors to enter into the mess, because when the seniors are not there, juniors can go and have the food. So your synchronization mechanism, when the seniors are not there in the critical session, it should allow the juniors to eat it. This is clear. But this is an example. So what I want to say is that the synchronization mechanism, if any one process is not ready to go to the critical session, it should not restrict the other process to enter into the critical session. So these are the two primary requirements of any process synchronization mechanism. So whatever the synchronization mechanism you are designing, it should go for these two solutions. One is it should provide the mutual exclusion, and it also should provide the progress. And then we will have the secondary requirements, because these requirements are not compulsory, but however it should provide. These are the primary requirements. Now let me discuss the two secondary requirements of any process synchronization mechanism. One is the bounded weight, okay, and another one is the portability. Are you able to understand? Now bounded weight meaning is that, let's take that, okay, process P1 has entered the critical session, okay, and again it has entered the critical session. It has entered the critical session. Now after some time, it should allow the process P2 to enter the critical session. So your synchronization mechanism, if it is allowing the process P1 to the critical session for some n number of times, then it should allow the process P2 to enter once. Is it clear? Suppose let's take that 5 times process P1 is entering to the critical session, at least it should allow the process P2 to enter once. Is it clear? There is a starvation problem, but this is okay. So you have the bounded weight. Each process should wait for a bounded amount of time to enter to the critical session. So when the process P1 has entered the critical session for 3 times, you should allow only at least once the process P2. Is it clear? This is the secondary requirement of any process synchronization. Then portability, whatever the process synchronization mechanism you have designed, it should not restrict only on one operating system or one hardware. It should be a generalized solution. Is it clear? Are you able to understand? So these are the 4 requirements of any process synchronization. 2 are the primary and 2 are the secondary. I hope you have understood what is a critical session, what is a race condition, and what is the requirements. If you still have any doubts related to this concept, feel free to ask me in the comment section. I will try to clear your doubts as early as possible. Thank you for watching the complete video. Have a nice day.